Okay, so you can go from coded to uncoded for both the mean and standard deviation. But here's the thing. What happens if they pull a little switcheroo on us? Sometimes they'll give us the coded totals and simply just expect us to reconstruct the original sum of x and sum of x squared. So how do we go about doing this now? Alright guys, so again, going a bit high level and just looking at the algebraic side. So let's say our code is y is equal to x minus a, okay? Now obviously that means that x is going to equal to y plus a, okay? So therefore our sum of x, okay, is going to equal the sum of y plus a, which therefore means that it's going to equal the sum of y plus the sum of a. Now what's the sum of a? Well, the sum of a is just going to be the values, the amount of values times the constant a. Okay, and to represent the amount of values, we're just going to say n. So that's going to be na. And obviously we know what y is. Well, y is equal to x minus a. So therefore our final kind of calculation is that the sum of x must necessarily equal the sum of x minus a plus na. Okay, this is just simply going through a bit of theory before the example, so this is just to give a background. I'm not trying to bamboozle you with, this kind of algebraic stuff. It's just to give you a bit more of intuition here. And next, for the sum of x squared, well, obviously, again, what does x equal? That equals y plus a. Sum of x squared, therefore, equals the sum of y plus a squared. Okay, and then you just expand that. And when you do expand that, what are you going to get? You're going to get the sum of y squared plus 2a times the sum of y plus na squared. Okay, kind of similar to before in a way, which therefore means when we simplify that down, knowing that that y is equal to x minus a, alright, we can say sum of x squared is going to equal the sum of x minus a squared plus 2a times the sum of x minus a plus na squared. Okay, but don't get too bamboozled with all that kind of algebraic stuff. That's just to give you a little introduction there. Okay, but let's get into the example where it really matters. Alright, so now we are going through an example. Okay, same running example with our data values. Now, what are we trying to illustrate here? Well, rule 3. Okay, it's all about recovering totals. Sum of x. That's what we're trying to recover here. Okay, so we're trying to prove that our sum of x is going to be 70. Our sum of x squared can equal 1020. Okay, so using y is equal to x minus 10, what are our values going to become? Well, we've already calculated that. Okay, so our values, same as before, or the original example, 0, 2, 4, 6, 8. Okay, perfect. Cool. So what does that mean here? Well, these are our coded values. This is the set y. So therefore, the sum of y, notice I'm doing it for the coded values first. The sum of y, we add these up. That's going to equal 20. Sum of y squared. Okay, well 0 plus 4 plus 16. Okay, and the sum of y squared, that's going to equal 120. Okay, so what does this mean here? Well, remember what y bar equals x bar minus 10. Okay, and okay, we know that, but we also know Now remember what the sum of x equals, okay? Going from the rules again, the sum of x is equal to the sum of x minus a plus na, okay? And this x minus a really just represents the code, okay, which is y. So we've worked that out. What's the sum of y? What's 20? What's n? N is 5. What's a? A is 10. Okay. So therefore, sum of x is going to equal 70. And as you can see, that is what we got in the beginning. Okay, so all this is reverse engineering. Again, not the kind of question you're going to get in an exam necessarily, but just to give you the intuition behind why this is. Next, sum of x squared. Okay, we know the sum of y squared is equal to 120, but we also know from our rules that we proved just now that the sum of x squared is equal to the sum x minus a squared, okay, plus 2a times the sum of x minus a plus a squared. And we know from before, this is just like saying x minus a is the same as y, right? So we're just going to plug that in. When we plug that in, okay, the sum of y squared, that's 120, and got 2a, so it's 2 times 10, times the sum of x minus a. Well, the sum of x minus a is the sum of y, which equals 20. Okay. N, 5, a squared, well, it's 100. So, add that all up together. That's 1020. What do you know? That's the same values we had in the beginning, right? Sum of x squared is equal to 1020, sum of x is equal to 70. So all we've done here is we've reverse engineered that process. So again, to recover sum of x squared, we know that the sum of x is equal to the sum of the coded values. Okay, sum of the coded values. Okay, plus na. Okay, number of values times constant. And sum of x squared, well, we just expanded that out. Okay, so to recover that, sum of the coded value squared, sum of the squared coded values, shall I say, and then 2a, sum of the coded values plus na squared. Then we get this. Okay, so a bit more algebraic, high level, whatever, but again, just to kind of try to illustrate a bit of intuition behind that. Alright guys, so now that you are able to recover those totals, which is a great exercise for understanding, there's actually a shortcut here that we can do as well. And that's where we don't really need to even decode first. And what that's going to allow us to do is get the standard deviation straight from the coded totals. So it's the same formula, but way less working out here. So what does that look like? Well, again here, if we use the coding y equals x minus a, we can say that the variance, okay, standard deviation squared, that's going to equal the sum of x minus a squared over n minus the sum of x minus a over n squared, okay? So that's going to be our formula there. And what that really boils down to and creates is the equation of the standard deviation is equal to the root of the sum of y squared over n minus the mean of the coded value squared, okay? So we intuitively know this, but it's just a way to kind of, I suppose, show the greater, wider picture here. So again, let's deploy an example here to see where this is going to be especially relevant. Alright guys, so same example, running example, 5 data values, cool. Now, what do we know here? We know that, let's see, using our previous example, okay, the sum of y is 20. The sum of y squared, again these are coded totals, 20 and 120. Okay. Now, let's use our formula here. So we know that the variance, okay, is going to equal the sum of x minus a squared over n, okay, and to be minus the sum of x minus a over n squared. Now again, you're probably thinking like, oh, you're trying to bamboozle us, it's all confusing. No, because what does this actually mean, this x minus a? This x minus a is simply y, right? Because remember, y is equal to x minus a. So, what our equation actually becomes here is the sum y squared over n minus the sum of yn over squared, and this is obviously mean, right? This over here is the coded mean. So we've just simplified it out, made things a lot more easy, and that's the thing, right? Whenever you've got an example, things become a lot more clear. So, therefore, what does this mean? Well, sum of y squared over n. What's our y squared? That's 120. What's our n? Our n is 5. Okay. Our mean is going to be 4. Okay, so we've got 4 squared there. So therefore, when we do this calculation, 120 over 5 minus 16, that's going to equal 8. Okay. So, therefore, the variance is going to equal 8, which means standard deviation is going to equal root 8, which is going to equal 2.83. We've got 3 significant figures. Okay. So what this represents, guys, is just an understanding of how to quickly find the standard deviation using coded totals. Okay, so as you can see here, we've got 2.83. Over here, our original answer was 2.83 as well. So all we've done again is we back tested, reverse engineered it. So the key point here, okay, is that yes, if we use our coded values first, okay, and we've showed that the coded values for our coding where it's just a shift, okay, that's important, where it's simply just a shift, the standard deviation is going to be the same. Let me repeat that. For a shift code, the standard deviation is going to be the same. And all we've done here is we've proven that. Alright, so this is where it gets interesting, guys, because so far everything has been revolving around one data set. But obviously, the examiner can sometimes give you 2 data sets. And this is less about the coding of values now, but more just about the case where they give you 2 data sets. So, what do you do when that happens? How do you navigate that? Okay, well, let's get into the example. I can show you how to do that. Alright, so here we are, rule 5, and this is all about combining data. Okay, now we know that group 1, which is what we have, okay, we know that our population size here is 5. Okay, we know the sum of x is 70. Sum of the square of those values is equal okay to 1020. Now let's imagine now we have a group 2. Now in group 2, let's say we have 3 values. Okay, where we have let's say 20, 22, and 24 as those values, right? So we can say that the sum of x2 is going to equal what? Well, that's going to equal 66. Now what about the square of those values? Let's square those values. It's going to equal 1460. Okay, so what can we say here? The combined mean is going to equal to the sum of x1 to the sum of x2 for n1 plus n2. Okay, so from this we can say that, okay, our combined mean here, guys, is going to equal to 70 plus 66 over 5 plus 3. Okay, and altogether, what does that give us? That gives us an answer of 17. Okay, now what about the standard deviation? The standard deviation combined, okay, similar concept. Okay, to sum of the squares at the top, but remember we have to minus the combined mean now because that's what we're working with. Okay, so we minus the combined mean, that's going to be minusing 17 squared. Okay, and we got our values here. Sum of x1 squared, x2 squared. So what's it going to give us? Let me see. June. That's going to give us root 21, which gives us standard deviation of 4.58, okay, to 3 significant figures. Okay, brilliant. So we've got that perfect. All you have to do here was really just work out the totals for each side and go from there. Okay. Now, interestingly enough, there's another concept that might be worth touching on. Okay. And that concept is all about, let me find it here. That concept is all about the fact that obviously you need the sum of x and sum of x squared for each group. Okay. Now, what if we're only given the combined mean and the standard deviation? Well, what do we do then? Well, we know that the sum of x is equal to n times the mean. Okay, because the mean is equal to the sum of x over n. Right? Brilliant. So that means our sum of x is equal to n times the mean. And for the sum of x squared, if we reverse engineer from the standard deviation formula, we know that the sum of x squared is going to equal to n times the standard deviation squared plus the mean squared. Okay? So that's just a way you can find the sum of x and sum of x squared if we're only given the mean and the standard deviation.